In this video, we will go through some preliminary remarks regarding probability. In particular, we will consider the question, what is probability? And why should we care? Let's start with the second question. Why is probability important to understand? First of all, probability is how we deal with variability. As we've said before, nothing is certain. Things are variable. We can never be completely sure. But not everything is equally likely. Some things are likely and expected, and some other uncertain things are less likely and unexpected. And we need to be able to handle this variability so that we make good decisions based on justified expectations. When are our expectations justified? When they reflect the actual probability that something will happen. More specifically, in a research context, there is the issue of variability coming from sampling. Sampling means because we can't measure everyone we're interested in, we have to sample and measure some people or some instances or some cases. And we want to be able to draw conclusions from our sample that will be valid for the whole population. That is, we want our conclusions to be valid for all those we didn't happen to sample. Would we get the same result if we had used another sample? If we run a study with 20 or 50 people and find something, would we have gotten the same finding with a different group of 20 or 50 people? This is very important in order to be able to make the right decision based on our study. So in general, we need to understand the variability of sampling, the variability that comes from sampling, what it implies for our conclusions, the implications of this sampling variability, which are inherently probabilistic. Now, what exactly is probability? There are different philosophical approaches to this question, and there are formal definitions. And we're not going to go into any of that. The question for us is how to think about probability so that we have reasonable intuitions and our thinking makes sense. So the basic idea is that probability refers to how likely something is to happen. But this is not very easy to think about. So the easier and equivalent way of thinking about it is how frequently something happens. So if there were many opportunities for an event to occur, how many of these would actually lead to the occurrence of the event? High probability means that something happens often. So it's a frequent occurrence. This does not mean that it's certain. We can never be certain. But we can expect it to happen. So a high probability event is something that doesn't surprise us when it happens. What about low probability? Well, that's the opposite. It's something that doesn't happen very often. So it's an infrequent event. That does not mean that it's impossible. It actually will happen, but not very frequently. So a low probability event is something unexpected that tends to surprise us when it does happen. It doesn't surprise us that it happens at all, but it surprises us more than a high probability event because it's expected less. And the question then arises, when exactly are low probability events expected? They're not zero probability, so they will happen at some point. Can we say something more about that? Let's ask this kind of question in a little more concrete context. It's not a special need education context, but it's something that's very easy to understand and think about. And then we'll go back to more relevant examples later in the course. So the easy question is, why don't I win the lottery? And there is also another question, if everybody can ask themselves, why don't I win the lottery? Then how come anyone wins the lottery? If it's so unlikely for any one of us, why is it likely for someone? So you're probably familiar with this type of lottery. In this particular case, there are 34 numbers, and you are supposed to pick 7 numbers and note these 7 numbers. And then there is some sort of draw that is a completely random event. There is some device that ensures that 7 out of 34 numbers are selected. So in this Norwegian case, and also in many other countries, there is a rotating device that uses air or something else to just mix up these numbered balls, and some of them are caught and roll out, and then you have the winners. So there are 7 numbers that are drawn at random, and if you happen to have picked exactly these 7 numbers, then you can win a lot of money. So that sounds enticing, and that's why people actually pay to do this. But as you probably know, you're not very likely to win. And why aren't you likely to win? Well, this can be answered by thinking of what it takes to have a winning sequence. If you are to win this game, this is necessary to happen. So when there are still all 34 balls inside that device, the one that comes out must be one of the 7 you have picked. So the odds of getting the first ball correct are 7 divided by 34. And after this, the following must happen. Of the 33 balls that are remaining in there, whichever one comes out must be one of the 6 left that you have guessed. And because you want both of these to be true, these have to be multiplied. And then there are 32 balls in there, and the one that comes out must be one of your 5 remaining choices, and so on and so forth. And the answer is, for all of this to happen so that you win, that you get the 7 balls correct by your single choice, the chances are 1 in about 5.5 million. To put this number in context, the chance of being hit by lightning in Norway are estimated to be about 1 in 150,000. And if you randomly dial completely random numbers on your phone, the chance of calling someone you know can be estimated to be about 1 in 167,000, assuming that you know about 600 people on average. And this is how many numbers are possible to ring in Norway. And I didn't make up these estimates. There are some published estimates for that. So how likely do you think it is to actually reach someone you know by randomly dialing? How likely do you think it is to be hit by lightning? Well, winning the lottery is way less likely than that. So that's why you don't win the lottery. An important note in this context is that this calculation doesn't take into account which numbers you selected, because it doesn't matter in any way. So any possible set of 7 numbers has exactly the same probability of winning. This means that these numbers are exactly equally likely to win as these numbers. And the reason I'm saying this is because these don't look very likely. These look more likely. These look more random, but that makes absolutely no difference. Any set of 7 numbers has exactly the same probability. So the probability of winning the lottery, a lottery of this sort, is best thought of if you're thinking of this sequence. You get a more accurate feeling than by thinking about these. Moreover, which ball comes out at any given instant does not depend on which one came out before, either in the same or in a previous draw. The random choice of numbers is independent and memoryless, regardless of what happened before or what happened in the immediately previous draw. So even if these numbers came up last week, this doesn't affect their likelihood of coming up again this week. So this should give you a better sense of how likely it is to win the lottery, although you already knew that you are not likely to win it at all. Which brings us to the next question. How come anyone wins if it is so unlikely? To answer this question, we have to think of a different approach. So if you were not just calling one random number, but if you dialed a million different random numbers, so you had a lot of time for many years, all you did was just dialing random numbers. After 1 million dials, would you expect to have reached someone you know? Probably more than one. If you played a million different 7-number sets, would you expect to win the lottery? You wouldn't be certain, but your chances would be much better. If you played all possible 7-number sets, then you'd be sure to win. But then, of course, you would lose money instead of winning. It would be too expensive to do that. But think of everything that's between selecting just one set of 7 numbers and all possible sets of 7 numbers. You move from very high uncertainty to near certainty. So whether or not you expect to win depends on how many times you try. Okay, now we're getting somewhere. How many times you try, it doesn't have to be you, it can be different people. So whether you can expect a winning set depends on how many people play. Actually, it depends on how many 7-number sets are chosen. But if everyone chooses just one, then the number of players determines how likely it is to have a winner. So large numbers, in this case, large number of trials, lead to a predictability of patterns of random low chance events. So here we have low chance events that are completely unpredictable, but if you have a large number of trials, then you can predict how often you can expect someone to win, approximately. You can calculate if you can expect a winner at every draw if you know how many sets of 7 numbers are played before the draw. You can never predict who will win, but you can predict how often someone will win. And for the research situation that we're interested in, this kind of probabilistic thinking is very, very useful because we're not interested in individual events, but we're interested in long-term outcomes of sets of events. So what's the point of all this? Is this about gambling? Well, although knowing about probabilities help with gambling, that's not long-term outcomes of random events or any kind of events that are variable. We don't control the variability, and we can think of them as being random. So any variability can be ascribed to a random process, and we treat our variable data as being random in some way, and then we can use ideas from probability to predict what can happen on the basis of these data. A bit closer to home, if we have a study based on data from a sample, so we study a special population and we want to understand a clinical population, for example, or we study the effects of an intervention. Either way, we don't study everyone. We use a sample of people and we measure something about them. So how far from the population value can we expect to be based on our sample? We'd like to draw a conclusion that is good for everyone in the population, including everyone we didn't measure. If we only measure a sample, how far from that population value can we expect to be? And how big a sample do we need in order to not be very far? This kind of question you can first think of in terms of something else you're familiar with, which is polling of voting preferences or voting intentions. So polling companies go and ask people what they plan to vote, who they plan to vote for, and then they report the results and give a margin of error. They say this is the percentage of votes for each party with a margin of plus or minus, for example, 2 percentage points or 1 or 5 percentage points. So they give a range within which they expect to be with respect to the actual voting intention for the rest of the population. And they can calculate how many people they have to go around and ask in order to have a range of their choice. Do they want to be certain to within 1 percentage point, or is it within 5 percentage points enough? So all of this comes from understanding the role of probability in affecting long-term outcomes of many events. And sampling is very, very important for us because all research is based on sampling. It's very rare that we can actually study the whole population that we're interested in. And more specifically, it's understanding probability that helps us decide if the finding from our study can be trusted and should be interpreted and generalized, or it should rather be ignored or augmented with more findings. So this is why probability is very important to understand, not just in the context of a statistics course, but in the context of understanding research and practice in special needs education.